Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this session. We were discussing the stepwise procedure for the design of a charge pump PLL. So, in the last class, in the last session, we looked at steps for designing a PLL given the unity gain frequency and the phase margin. So, our PLL was this with phase frequency detector, and for the given phase frequency detector, the output of the phase frequency detector fed to the charge pump using up and down pulses. The charge pump output was given to a loop filter with the resistor R1, C1 capacitor and C2 capacitor. Okay. And the output of the loop filter was given to voltage controlled oscillator. And in this particular case, we had our output frequency feeding back at the input. So, this is our input, this is our output. The output of the charge pump is current, small ICP, the voltage was V control, right. The small signal model of this particular PLL was this, where you subtract the phase error in the PFT, and the gain of the PFT was 1 over 2 pi, followed by the charge pump whose gain was ICP. ICP went through the loop filter with R C1 and C2 here, and the gain of the VCO was K VCO over S for the phase. Okay. So, I want to show the difference between this PLL and the PLL where you have frequency multiplication. Actually, the procedure remains same for the design of the PLL, finding all other components. The only thing which changes the loop gain. So, here we considered as phi in and phi out. This is often also written as phi ref if this is the reference frequency. Okay. So, you get phase error here, and then output of the phase error detector you can say this is VPD and this is small ICP, this is V control. Okay. So, what we said in the procedure was that you need to be given, this is important, given unity gain frequency omega u and phase margin phi m. The steps included: first, the calculation of C1 by C2 ratio depending on your phase margin. So, we did that, and this turned out to be 2 times 10 square phi m plus 10 phi m times the square root of 1 plus 10 square phi m, where phi m is the phase margin. Okay. Second step was, given that our C1 by C2 ratio, we can find omega z, which was omega u divided by 1 plus C1 by C2. Third step was, given omega z and choose R. Now, you can say how will you choose R? Well, that is going to depend on the noise, which will be the topic of discussion in the coming sessions. So, choose resistor R, this will give you C1 as omega z times R. Once you know C1, your C2 is also known, because this constant C1 by C2 is already known. So, C2 is C1 by Kc. Then using the fact that at the unity gain frequency your modulus of loop gain is equal to 1, right. This is equal to 1, it implies this is the condition for the fourth variable which we would like to have. Okay. Given this is equal to 1 and given KVCO also, KVCO is a parameter which you will get while designing the oscillator. So, KVCO is known. So, in the loop gain KVCO is known and other parameters are known. So, then your ICP is simply equal to 2 pi times C2 divided by KVCO into omega u square root of 1 plus omega u square by omega p3 square divided by 1 plus omega u square by omega z square, where your omega p3 is equal to 1 divided by r C1 C2 divided by C1 plus C2 and omega z is equal to 1 by r C1. If you wonder how you get this equation, well, loop gain of the PLL, just reminding you, loop gain of the PLL is equal to ICP by 2 pi into 1 by s square C1 plus C2 times 1 plus SR C1 whole divided by 1 plus SR C1 C2 by C1 plus C2 into KVCO. So, I will just write KVCO here, right. So, what we are doing is we are making that modulus of loop gain at omega u is equal to 1. Okay. So, when you do that here, first I wrote the final equation, but now just to help you that how you will find it, well, this is equal to 1, which implies ICP by 2 pi times KVCO whole divided by omega u square C1 plus C2 square root of 1 plus omega u square by omega z square divided by 1 plus omega u square by omega p3 square. This is equal to 1. So, now you see that ICP you will just have 2 omega, but this is going to be C1 plus C2 here, right, and you just equate it back. This leads to this value. Okay. So, which will give you the ICP. So, you think about it, unity gain frequency and phase margin are the two numbers which you will start with. You will choose R, or you can say you also know R. By the way, R is a variable, R can vary it does not have to depend on omega u and phase margin, you can choose your R, and KVCO is another parameter which you will get during the process of the design. What you found is C1, C2, ICP. Okay. So, based on these you will get the loop gain for the desired unity gain frequency and phase margin. Now, if this PLL changes from PLL to clock multiplier, when you are changing the frequency, how does analysis change? Well, it is very simple. I do not have to do anything here, just make one simple change. So, in place of the frequency we out connecting to input to the feedback, here I have a divide by n frequency divider, and when I have a frequency divider in the PLL block, I am going to have a phase divider in the small signal block. Okay. So, the new loop gain is going to be ICP by 2 pi into 1 by S C1 plus C2, 1 plus SR C1, 1 plus SR C1 C2 by C1 plus C2 times KVCO over S into 1 by N. So, you measure the loop gain by going across around the loop and coming it back. So, this is your loop gain. So, the loop gain has an additional factor of 1 over N. Same procedure, no changes, given omega u and phase margin, you will find C1 by C2. Second, once you know C1 by C2, you find omega z, right, that is what you did. Third step, you choose R and get C1 and C2. Fourth, given KVCO, you get ICP. Okay. The only difference here now, in your ICP, you are going to have in this transfer function, you will have N also. So, if you have in denominator, you have N, in the numerator, you will get N times. So, what we get here is, just do it like this, into this is N times. So, you get the current. Okay. So, whether it is a clock multiplier or it is a simple you can say a frequency buffer, where the output frequency is same as input frequency, the design procedure remains the same, right. In the second case, as you see, the output frequency is N times the input frequency. Okay. So, if I design in this particular manner and I choose certain variables, what thing I am assuring you is the following. You look at you found all the parameters, you feed those parameters back into the loop gain expression and draw the Bode plot for modulus of loop gain. Okay. So, one thing is, if your phase margin is going to be positive, your omega u will be in between your omega z and omega p3. Okay. Omega u may be somewhere here. It is actually the geometric mean of omega z and omega p3. I am drawing this thing in log scale right now. So, what I am going to see, the characteristics like this. Okay. So, here you will see minus 40 dB per decade, here you will see minus 20 dB per decade, and this is going to be again minus 40 dB per decade. Okay. Corresponding to the magnitude plot, you look at the phase plot. Okay, let me just plot it till here, angle of loop gain. So, at the unity gain frequency, at the 0 frequency, you will have a phase addition of 45 degree. You are going to start from minus 180 degree. Okay. So, this is minus 180 degree, it will be minus 135 degree here, and then whatever phase margin you desire, you will get this phase margin with maximally flat at unity gain frequency. Okay. This is what you will get. This is maximally flat and your phase margin is phi m, whatever you desire. Okay. So, our aim was to choose the parameters C1, C2 and your R parameter, the placement of omega z and omega u in such a way that your magnitude of that you get your phase response as maximally flat at the unity gain frequency. In that way, any small changes in the values of R and C, right? Well, C1, if C1 and C2 both change by the same value, your phase margin does not change. If your R and C changes by a small amount, you can say if your unity gain frequency changes by a small amount, then your phase margin will not degrade that much. Okay. Now, just a simple calculation with the phase margin as calculated from this expression. What I want is j omega u equal to 1. This is, by the way, an approximation which I am going to do, assuming that omega u is much greater than omega z and much lesser than omega p3. So, if I keep that assumption, then I can simplify this, okay, and I can neglect this part. So, if I do that and I want to calculate what my unity gain frequency is, then you will see this is going to be ICP by 2 pi divided by omega u square C1 plus C2, okay, and this term is going to dominate. Okay. So, if this term dominates, what I am going to get here is omega u by omega z. The denominator is insignificant because our omega u is much smaller than omega p3, okay, times k VCO by n. This is equal to 1. So, to a simple approximation, you can say that omega u unity gain frequency, this goes off. So, what you get here is well, ICP by 2 pi 1 by omega z, which is R C1 divided by C1 plus C2 k VCO over n. You can say this is R C1, yeah, this is equal to ICP R k VCO divided by 2 pi n into 1 divided by 1 plus C2 by C1. So, I will just write it like this. This is an approximation, by the way. Unity gain frequency 1 plus C2 by C1. Okay. So, you can calculate unity gain frequency, and what you see here is that your unity gain frequency is proportional to R. So, just think about it, if your R varies slightly from your desired value, your unity gain frequency will vary, but your C1 by C2 remains same. So, your phase margin will remain same, there is quite less deviation there. Okay. So, this is the standard procedure to design a simple charge pump PLL or a charge pump clock multiplier. Okay. Thank you.